Oh, really? I haven't done.
I haven't done 12.
I've done 12, but.
I know, I just know.
Mm-hmm.
I'll just wait. Did he post it?
It's the Idella reading. Took one of them off. So starting out in Wednesday? 10:20. That's one of them. Okay. I have a question. I can do the compound criteria wrapping. It's homework. Homework. We did it in homework. 3.7. Yeah. No. Is it? Square both sides. No, I don't understand. I usually write myself little notes. So I know what I'm doing. I got to this point when I was doing. And that I got. I don't like why. And then on the other one, like this one, I guess. I don't. That's not. AQ, it is number 15. That one, the proof that AQ is even, and B is even, it's number 15.
That's the issue, right? That was last time.
Yes.
You know, it's not going to do me to look at this answer, not enough. That's why I don't bother trying to.
I'm working on it right now. Left-hand side. This is actually.
Oh,
I'm gonna ask this. Yeah, I still got number 8. I did all the homework. I just didn't do number 8. Blackboard.
Megan. Here. Elsa. Here. Morgan. Here. Allison. Allison. Katie.
She said she'll be a little late, but she will be here.
Okay. Jesse. Jesse. Leah. Here. Catherine. Here. Curtis.
Here.
All right, do you have any question about the homework?
Did you say you did want us to do number 6 or you did not?
Number 6. let me take a look. Which section is that? Which chapter?
4.3.
4.3. You don't have to do that one. If you did, it's fine. But if you, let me see. Did I cross that out?
It's on the listed problems, but then when we go to turn the homework in, it's not one of the problems that it has there. If that makes sense.
Yeah. I think I delete that. Yes, from the homework list. But it was typed up in the document, right? But PDF. You didn't have to do that.
Gotcha. Thank you.
I mean, if you did that, it's not a big deal. But I mean, you didn't have to do that one because it's the same as number 8. Any other question?
Number 8 on 4.3.
Number 8.
Yes.
Number 8. Well, I can go over that example we did in class. What I did was 2 to the 2n is divisible by 4. So we can look at that one more time. I think the confusion, I got a few emails about number 17. Number 8 actually is easier than number 17. So number 8 is much like still trying to prove an equation. So let's look at this example here. Okay, so this question is a divisibility question. You want to prove a number is divisible by 4. And what's the definition of divisibility? If you say A divides B, what does that mean? What's the definition of that? A divides B.
B equals A times some integer.
Yes, good. So B equals A times some integer. Usually, when you write it down, you will use a variable to represent that integer. So A times K here. They are equivalent. So whenever you see A divides B, it means B equals A times some integer. The other way is also true. If you can write B as A times some integer, then you can say A divides B. So that's the definition of divisibility. When you go back to number 8, number we want to prove is 8. 4, this is like 4 divides. When you say 5 to the n minus 1 is divisible by 4, it's like saying, it's asking you to prove 4 divides 5n minus 1. That's what we want to prove. So by the definition, the a will be 4, here b will be 5 to the n minus 1. You need to write 5 to the n minus 1 equals 4 times some integer. Excuse me. So this is the integer you have to find yourself. This integer doesn't have to be a number. It could be a variable. Just in other words, it's like how do you factor 4 out of there? So because apparently you cannot, by looking at this expression, you cannot factor 4 out of 5n to minus 1. You have to use something else to do it. So here we use mathematical induction. So this is exactly the same as the example we did in class. That's the example we did. We want to prove 2 to the 2n minus 1 is divisible by 3. In other words, I need to factor 3 out of there, which I can't. So that's why I do mathematical induction. N equals 1, so you plug 1 in there. So that should be easy. You're going to do exactly the same thing. So the homework question, you can follow this example we did. The difference is what you have is 5 to the n minus 1 instead of 2 to the 2n minus 1. And you have divisible by 4 instead of divisible by 3. But the way you do the question will be exactly the same. So we did the basic step. In your case, you have to replace your n by 0 instead of 1 because I have n greater than or equal to 1. In your case, your n is greater than or equal to 0. So when you do your basic step, you have to replace your n by 0. Let n be 0. Replace n with 0 and show that it's divisible by 4. In the inductive step, it should be the same. We have, so that's the step you have to memorize. Whenever we do mathematical induction, you always assume whatever they want you to prove is true for n equal to k. So this is the one they want me to prove. So I'm going to replace the n with k. I got 2 to the 2k minus 1 is divisible by 3. Exactly just copying that by changing n to k. So you're going to do the same thing. You're going to replace your n with k and replace 5 to the k minus 1 is divisible by 4. And the important step is to prove when you replace the n with k plus 1, you're going to get 2 to the 2 times k plus 1 minus 1. You have to prove it's still going to be divisible by 3. In your case, when you replace this n by k plus 1, you're going to get 5 to k plus 1 minus 1 is divisible by 4. So you have to prove that. And how do you prove that? That is algebra. We're going to do algebra work. But this is the one I need to prove. You put these two together and compare them. That's the one I know. I know 2 to the 2k minus 1 is divisible by 3. I want to prove 2 to the 2k plus times k plus 1 minus 1 is divisible by 3. So when I look at them, I use algebra. Again, this can be imitated in your case. So first I have to distribute 2. In your case, you don't have to distribute 2 because you don't have a 2 there. You just have k plus 1 there. You don't have to distribute anything. So your case is easier than my case. If I distribute 2, I got 2 raised to 2k plus 2. And when I compare 2 to the 2k plus 2 and 2 to the 2k, I realize that in order to get something like that, I'm going to use the algebra formula. 2 to the 2k plus 2 is right here. So that's the algebra formula we're using. Okay, so in algebra, we have this formula. X to the m plus n power equals x to the m times x to the n. So in D05 class and in 1200 class, you will learn these formulas like twice. In calculus class, you also use these formulas. So you should have seen these formulas many times. So okay, but when we use them in algebra class or in calculus class, most of the time you're using the other way. X to the m times x to the n equals x to the m plus n, adding the exponents. I think in calculus, sometimes you may have to do this way too. And so that's what I'm trying to do. Well, because I saw I have to find something relation between 2 to the 2k plus 2 and 2 to the 2k. So that's what I did. Okay, I found out using this formula. 2 to the 2k plus 2 is equal to 2 to the 2k times 2 squared. Because these are two exponents. Adding exponents, you're going to get that. But you can also split the exponent 2k plus 2 as 2k, 2 to the 2k times 2 to the 2. So that's the formula. You have to learn to use it backwards. And after that, 2 squared is equal to 4. So I found a relation between these two expressions. The one I already know, the one in the assumption, 2 to the 2k minus 1, and the one I need to prove, 2 to the 2k plus 2. So I found out, okay, if I take 2 to the 2k multiplied by 4, I would get this. Or in the other words, this is equal to 2 to the 2k times 4. So that's what I did. I take this. So in your case, you will be taking 5 to the k plus 1. 5 to the k plus 1 minus 1 is equal to, use the formula. We will get 2 to the 2k times 2 squared. That's the algebra formula. And 2 squared because it's equal to 4. So I'll go ahead and simplify this part right here as 4. So I got 4 times 2 to the 2k minus 1, which is my next step here. Yes, I can go.
Did you say we had to write out that like P of K is true? Like, do you want us to state that every single time in the inductive steps?
In the final step, yes. I mean, when you do it, you have to know this, right? If you don't know what you're proving, you will. So this is something I always write it down at the bottom of the page or put it on the scratch paper so I know what I need to prove, right?
Yeah, but just like P of K, where you just like, it says assume P of K is true, and before you move on to P of K plus 1.
You don't have to, because
Okay.
this one is P of K. I didn't mention
Yeah.
that terminology was symbol. So in the textbook, they call this P of K. What does P of K means? P means property. K means N equals K. So pretty much P of K means what we always say. Assume the formula, P means the property. Assume the property is true for N equal to K. You don't have to say assume P of K is true. You can go ahead and just say assume 2 of 2K minus 1 is divisible by 3. Because what's P? It's the property they want you to prove. Okay? Technically, this sentence right here, this whole sentence is the same as P of K. So you don't really have to add another sentence, say, assume P of K is true. Then 2 to the 2K minus 1 is divisible by 3. You don't need to do that. You can go ahead and just assume that. So when you get over here, and like I said, I'm just going to continue from here and write it out. So when you get this to this step, you're going to get 4 times 2 to the 2K. 2 because 2 squared is 4. And what is 2 to the 2K? That goes back to the beginning. You have to find out what 2 to the 2K is. That's in our assumption. Because the assumption says 2 to the 2K minus 1 is divisible by 3. By using the definition I just went over, that means you can factor 3 out of 2 to the 2K minus 1, which gives you this expression right here. 2 to the 2K minus 1 equals 3m. So you may wonder, say, if I just went ahead and write this down, you may wonder, why are you doing that? Okay, but a lot of times, that's what we notice, that's what we have to do most of the time. Whenever you see a sentence like something is divisible by something, you should always change it to its definition, the equation form. You're always going to use the definition to immediately change A divides B to an equation, because this is much easier to prove. B equals A times some integer. So that's what I did. So whenever I see something is divisible by something, I'm going to write it in the equation form by the definition. So this is 2 to the 2K minus 1 equals 3 times the integer. And that's when I plug it back in there. When I plug back in here, so I will get, write it down. When I see 2 to the 2K, by the definition and assumption, 2 to the 2K is equal to 3m plus 1. And I can use algebra to get 12m plus 3 minus 1, which is equal to 12m plus 3. And we can factor out the 3. And we're done. Now, let me, so here when I explain this question, I kind of like start from telling you what my thinking process is. When you write on the problem, so here is what you wrote down. So n equals 1 or n equals 0. Plug 1 into the property, the statement you want to prove. Or 0 plugged in there. You want to prove that. Whatever is divisible by 3 or by 4. In the inductive step, what Curtis said, assume P of K is true. But you can skip that sentence. Just go ahead and put, what's P of K? What's the property where n equals k? Well, 2 to the 2k minus 1 is divisible by 3. That's P of k. So you can go ahead and just write down, assume 2 of 2k minus 1 is divisible by 3. In your case, in your homework, it will be, assume 5 to the k minus 1 is divisible by 4. Whatever the statement is there, you just replace the n with k. And the next step is, by using the definition of divisibility, 2 to the 2k minus 1 equals 3 times the integer. I use the m. Usually we use k. I didn't use k here because I already used the k. So you cannot use k again. So that's why I use the m. And after that, I add 1 to both sides. I get 2 to the k by itself equals 3m plus 1 because I know I did this work before on my scratch paper. I know I need to do substitution later. I need to replace 2 to the k. That's why I get 2 to the k by itself. So now the next step is, when I get it here, I will, this is what, I'm going to go ahead and copy those. So what I have is 2 to the 2k times 1 minus 1 equals, by using algebra, 2 to the 2k plus 2 equals minus 1. 2 to the 2k times 2 squared minus 1. So I'm going to add all of that. So this, where does this come from? That's P of k plus 1. The property for n equal to k plus 1. So if you look at over here, replacing that m with k plus 1, that's how I got this expression. And I use algebra. All that whole part, the whole thing right here is algebra. So that's why I'm saying at the beginning of this last Monday, I went over some algebra formulas because we do a lot of algebra here. So I use algebra to modify distributed 2. I get 2k plus 2. And then I use the algebra formula, which is this one, to get 2 to the 2k times 2 squared. This plus is changed to times 2 squared. And use algebra, 2 squared is equal to 4. And then I use substitution. What's 2 to the 2k? I already got it by itself. 3m plus 1. I replace 2 to the 2k by 3m plus 1. And using algebra, distribute, combining like terms, and factoring. That's how I got 3 times 4m plus 1. And how did I get this expression? This expression is the same as what I started with. You see, equal. So which means what I started with, I'm going to go ahead and move that down here so you can see better. 2 to the 2 times k plus 1 minus 1 can be expressed in this expression, 3 times 4m plus 1. They should be equal. They're the same thing. Okay? So originally, I wanted to prove this expression is divisible by 3, which I cannot factor 3. But now, since I proved this expression is the same as that expression, and look, that is divisible by 3, right? Okay, so that's why we're done. And you can see 3 goes in there. How many times? 4m plus 1 times. And that m is an integer. What's that m? M is right there. How many times 3 goes into 2 to 2k minus 1? Because this m exists. If this m exists, I'll just take that, multiply by 4 plus 1. That gives us how many times 3 goes into this expression here. Okay, so that is the idea of the proof. And when you do your homework, factor it in. It should be a little bit easier than this, but the idea is the same. So you do have to use this formula backwards. Well, not really backwards. In algebra, you do this way, but this is in algebra class. That's what you do. In this class, in discrete math, you do this way. When you see addition of 2 exponents, you can split it as x to the first exponent times x to the second exponent. The reason you want to do that is because you've got to find a relation between these two, 2k plus 2 and 2k. Okay, any other question? Number 17, it's inequalities. So it's a little bit different from this, but you can still do substitution, but usually the way we talked about last time is you are not trying to, from P of K, the assumption, this is what we call assumption. When you replace n equals k, usually you would get something like A is a number is less than another number. But in P of k plus 1, that is the one you want to prove. The formula or statement property when n equals k plus 2. They want you to actually prove A is less than C, right? So how would you prove A is less than this number C when you already know A is smaller than the number B? Well, remember what we said?
B is smaller than C.
Yes, that's right. Very good. So this is something you gotta use. All you have to do is, if you can show me B is smaller than C, well, combining these two, you already know A is smaller than B, and you proved B is smaller than C. Of course, that tells you A is smaller than C. So you don't have to show B is equal to C. You just need to show B is smaller than C. Okay. So if you still have trouble doing this, and you can send me an email about number 17, and I can help you with that. All right. And just a reminder, the second practice exam you can also do next Monday. And the second exam is 2 weeks from today. Now, today we're going to continue chapter 5. So I have talked about the definition of set, what a set is, and I also introduced a few symbols, another new concept called subset. Let's go over those concepts quickly here. So we talk about, I said in 5.1 there are a lot of definitions of symbols you have to memorize. The first thing, sketch notation, that's something everybody's familiar with. You use curly brackets, and you could list all of them if it's possible, if there's a pattern. But most of the time, you can't list all of them. If you want to describe if the elements of the set is all real numbers greater than 31, you really cannot list any of them, because that includes 1.1, 1.11, 1.111, 1.111, 1.12, 1.09. So you cannot really list them. But in that case, you just describe them this way. Put x is a real number, vertical line, and x is greater than or equal to 1. And usually we use the capital letter to represent a set. So it's easier for us to refer back to it. So we don't have to say this set and that set, this set and that set. So you can just say a set A, set B. So in this case, we talk about an element. And that's an argument you have to do later a proof. Homework question you have, in this section we only have one type of proof question. That's like asking to prove subsets. And so before we talk about the definition, go over the definition of subset, we look at the definition of element. When you have a set, we say, okay, 1 is in the set. Or you can call 1 is an element of the set. Or in the first case, 3.5 is, of course, 3.5 is greater than or equal to 1, and 3.5 is a real number. So we say 3.5 is an element of A. But that whole sentence, words, is an element of A can be replaced with a simple around E, capital letter E, but it's like around and not straight lines. So 3.5 belongs to A, where 3.5 is the element of A, where 3.5 is in A. So you can read it many ways. Okay, so it's obvious that this is something you don't really have to define. So anything in the set is an element or a member. But subset is something we have to memorize the definition here. But what is a subset? When you have two sets, a set A is a subset of B, a set B. If and only if every element or every member of A is an element of B. Simply in putting symbols, any element, any X in A, X is also in B. That's what it is. And I gave you an example last time. Those three sets, A, B, C. So A has 3 elements, 1, 2, 3. B has 4 elements, 1, 2, 3, 5. C has 3 elements, 2, 3, 4. As we check, and we find out A is a subset of B because thinking about the definition, that's that is something you do have to memorize. That are the definition right here. That memorize those symbols. But I think when you memorize, probably it's better to use English sentences to help you memorize. But when you write down the proof, we would like you to use symbols. So when you write down the proof, that's what you use. But when you memorize it, memorizing the sentence will be easier for you to remember. So pretty much, what's a subset? If every element of A is also an element of B, then it's called a subset. In real life, you could have, say, like if I walk into another education class and I found all my students are also in that education class, it's kind of like a subset. I may say in real life, I may say, okay, looks like every student of my discrete math is also a student of this education class. That is a subset. Because that's exactly the definition. Every element, so in our case, every student of A means discrete math. Every student of discrete math is also a student of this education class. So that we can call it a subset. But this education class may have some other students, or may not, or may be the same, but we can still say it's a subset. So the symbol we use for subset is like sideways U, but you put an equal sign there. Because sometimes they could be equal. The idea of this is similar to the symbol of less than equal to. If you remember, say, 5 is less than 10, but you can also put 5 is less than or equal to 10, right? Because this symbol just means less than or equal. We put them together. We create this new symbol. The same idea for our subset. So this means strictly less subset. Like 5 is strictly less than 10. But you could put, if it's 10, 10 is less than or equal to 10. So it could be equal. And so the same thing, if we have or means this, okay, means or equal. So two sets, they could be equal or they could be small. So let me give you that example that I mentioned. Suppose I have my discrete math class. I have, let's say, James, Elena, and Danielle, and Austin. So I have these 4 students in my class here. And then I walk into another education class. I found that James is there, and Elena is there, Danielle is there, and Austin is there. Maybe there's another student, say Mary, is also there. And then this is the time I can say, well, I found out, okay, well, every student of my class is also a student of that class. That's exactly the subset. Okay. In this case, I don't have to put an equal sign there. We do this, okay? So if you say, well, they are not equal, because E has one more student. They are not, D and E are not equal. We don't have exactly the same number of the same students. You can put a line through that, which means they are not equal. Or you can just put D is, we don't say strictly less than, we say a proper subset. So in this case, if D is a subset and D is not equal to E, then we say D is a proper subset. D is a proper subset of E. But maybe, suppose I can, if I change E, if Mary is not in the education class either, maybe we can call it E prime has J, E, D, A. Well, in this case, look, the discrete math class students are exactly the same students with the education class. Exactly the same, right? In this case, you could put they are equal. Or you could also put D is subset of E prime. Because even if they equal, it still fits the definition of subset. What's the definition of subset again? Every element of D, in our case, every element of D is also an element of E prime, right? Well, when I check, James is in education, Elena is in education, Danielle is in education, and Austin is in education. That means the definition of subset. So you can still use this symbol. But I cannot use which symbol? Can I use this symbol? No, because this means what? Proper subset? What's the definition of proper? They cannot be equal. So the formal definition, I don't really think you need to memorize it if you understand this. The formal definition means D is a subset of E and D is not equal to E. Okay? If they are equal, you cannot say it's a proper subset. So E has to have something that is not in D. So Mary, say if education class has Mary, but Mary is not in the discrete math class, then you can say D is a proper subset. Okay, most of the time we say subset, but if you want to say it backwards, you can say E is a superset if you want. But like I said, most of the time we use subset. So the symbol, just like inequalities, you have less than, equal to. When you switch them, say 5 is less than 10, you can switch them to get 10 is greater than 5, right? So we can do the same thing. In this case, we have D is a subset of E. If I switch them, if I put E first, what do you put? Turn it around, right? So you switch this sideways view in the other direction. So E contains D. Well, E is a superset of D. But like I said, most of the time we prefer this symbol, subset. Or you can put an equal sign if you want. All right, so that's the definition of subset. And like I said, please memorize this definition because we're going to use this in the proof later. And for some reason, in the past, students always have trouble doing the proof of this subset. And I'm not really sure why, because if you memorize this definition, that's all you have to do. So for example, but in this case, it's very easy, right? So let's, if I want you to prove D is a subset of E, what would you do? I explained it, but if I want you to write down a proof, say prove D is a subset of E. So the definition you have to prove. Well, maybe I can just start with writing the proof. This is what you, like what James just said. Okay, the definition of subset is every. I'm going to write down the English sentence, but when you do the homework, you can use symbols. So every element of D is an element of E. That's what we need to prove, right? The symbols will be, how do you put in symbols? For any, how do you put this in symbols? Every element of D is an element of E. For every, X in D, you have to introduce a variable to represent. Because every element, how would you write every element? You can't, right? You just have to use a variable. Because how many elements do we have here? 4 elements. D has 4 elements. So when you try to describe every element, you got to use a variable. So for every element of D, we got to prove X is also in E. Does everyone understand this? Does everyone have a question about this? How I convert the sentence to symbols? No? Is that clear? Okay. You do have to introduce a variable x. What is this x? X represents every element. Okay, that sentence right there. How do you describe every element? It's a variable x. In algebra class, we say, okay, x is an unknown, but this is something new. X doesn't always have to represent unknown. It can represent something that changes. That's why we call it variable. So this x represents every single element here, which can change from J to E to A. So when I write, this is what I need to prove. So how do I write on the proof? Every element, right? So, okay, what is possibility for x? It's going to be J. So I checked, okay, I picked J from D. Since J is in E, well, maybe I should add a sentence. Well, let me do this way here. So usually the problems you're going to do, you won't be given these elements listed. So that's the difficult part. Right here, we do know what elements are in D. So that I can say, okay, since x possibly could be equal to J, E, D, A, and J is in E, E is in E, D is in E, and A is in E. Therefore, every element of D is an element of E. Right? So that's what we need to prove. Every x from D. So what I went to check is, okay, what kind of elements do we have for x? What kind of elements are in D? J, E, D, A. So I check every single one to make sure every single one of them is also in E, the superset E. So I found out, yes, James is in E, education. Elena is in E. Daniel is in E, and Austin is in E. It's sort of like I'm hosting the list of the students' names. I have a piece of paper with students' name on it. I went to the education class. I look. James, okay, in there. Elena, yes, in there. Danielle, in there. Austin, in there. So after I put check mark, okay, every single one is in the education class. That's when I say, okay, every element in D is an element of E. Therefore, I can say D is a subset of E. At a conclusion there. And that English sentence, you don't have to put it there. I'm writing it down to help you memorize the symbols. That sentence is the same symbols. It's not like I'm saying, okay, when I write down a proof, can I use sentences? Yes, you can use sentences, but we don't really do that in the proof of set theory, and we like you to use the symbols. I mean, I wouldn't mark if you everything you say is correct in sentences, I will still mark you right, but we want you to use symbols. All right. So first, again, like I said, when you actually do the problems, you're not going to know what elements are in D, what elements are in E, so you cannot see them. Well, how do we prove that? So we are going to talk about that proof question later. Now, that's any question? So subset is a very important concept in discrete math, in set theory. So now let's look at part 3, operations. And I think that you may have learned this in your other classes. So we're going to talk about union, intersection, difference, and complements, those 4 operations. The first one we're going to talk about is union. When you are given 2 sets, I'm going to go ahead and leave a little bit of space so you can write down the definition. I'm going to go ahead and look at these 4 together, 4 operations together. Union, intersection, and difference, and complements. Complement. All right. When you're given 2 sets, you can do operations just like numbers. When you're given two numbers, you can add, subtract them, multiply them, divide them. Those are operations we do it for numbers. So for sets, let me start with, give you an example. That's on page 261. We're going to use example to explain this. And later you can write down the definitions there. And also you have to memorize the definitions for especially the first two. I think I'm just going to ask you to, do the proofs of union in this section. So I won't ask you to do proofs of difference or complement. Let's look at the example. We have a universal set. In a second, I'll explain what a universal set is. The universal set is like all the operations will be, it's like the elements, all of the elements we're going to consider. We're not going to consider anything out of these. We have A, B, C, D, E, F, G. So we know we still have other like H, I, J, K, L, M, N, but we're not going to talk about them. So these are all the elements we're going to talk about. And A has A, C, E, G. B has elements of D, E, F, G. Okay. First question is union. The symbol for union is the same as the letter U, so it could be a little bit confusing. So this U means the set, but this U means union. What's the definition of union? Have you learned the union before? I mean, you're in the statistics class you have, right? Elena, do you remember how we do union? Or Austin or Daniel? Daniel? Huh?
One of them has to be in either set.
Yeah, so what would you think the answer is for this question, A union B? Did you say E and G? That's not the union. That's intersection. Does anybody know the answer for the union?
It would be everything together. So A, C, D, E, F, G.
Oh, D, E, F.
D, yeah.
Yes, D. All right. So look what she put in here. Everything, either in A or in B. So the definition of union, when you see this U, letter U, it's the same as the English word what?
And
In. Huh? Or. Like or. Okay. And is for intersection. Upside down U. When you see and, it's and. Do you remember in chapter 1 when we talk about logics? We had what? Compound statements, conjunction, disjunction. Do you remember what we used there? It were rain and it was snow. What was the symbol we used? Rain and snow. Like that, right? Okay. It's the same, similar. Instead of upside down V, we use upside down U. It's kind of similar. One thing is, pointing. The other one is round. So they are kind of similar. But over there, we're talking about statements, rain and snow. Over here, we're not talking about statements. We're talking about elements. So they're a little different. Well, so that's when you say and, you got to find those letters not only in A but also in B. In A and in B, which will be E and G. So look, they're very different. Union, we do have this concept a lot. I mean, in algebra class, you also have this idea, compound statements. I don't know if you remember. So sometimes in real life, we also say that, and or, right? So presidential candidates have to be born in America and, right, over 35. So it's and. But if you say, okay, amusement parks, they give discounts to toddlers or seniors, right? But then you have to use the word or. They're different, and or. And is stronger. It has stronger requirements. That means you have to meet both requirements. So anything you put in here has to be in A and in B. But what do you put in union? You only have to appear once, either in A. So like A is not in B. You don't have to worry about that. As long as you're in set A, you are in the union. Okay? So union has more elements. What you can say the requirement is not as strong as and. C is not in B, but it's still in the union. D is not in A, still in the union. E is in both, still in the union. Union includes everything. It appears at least once. At least once. Could be twice, could be once. But in intersection, it has to be twice. If you got two sets, it has to be twice. See? In A and B. In A and in B. But over here, well, if you appear twice, E and G, of course, that's better, more than qualified. But it doesn't have to, okay? So make sure you understand remember the difference between or and, union and intersection. Don't confuse them. Again, like I said before, when we talk about chapter 1, many times in real life, we don't distinguish them. We think they're the same, but they're not the same. Go back to review what we learned before. Rain and snow, which means you see both, right? But rain or snow, how many cases does it include? If I make a claim at the beginning of the day, I say, it's going to rain or snow. How many cases are possible? It could be rain, but no snow. I'll put and no snow, and no snow. I could mean snow and no rain, right? Okay, no rain. There is another third case. What's the third case?
No rain and no snow.
No rain, no snow? When I say it is going to rain or snow today.
It rains and snows?
Yes, that's right. It rains and snows. It includes rain and snow. Did you see that? So union includes intersection, or includes and. Okay, disjunction includes a conjunction. All right? Yes? Is that right? And I can give you another example, real life example. So, for example, the presidential candidate, you have to be born in America or born in USA and over 35. So the word between them is and, which means you have to meet both. But what if I say one or two? If you were born in America or you are over 35, what kind of cases will include? Which people will possibly? 3 cases. Case 1, you will find someone who was born in USA, and not less than we go to 35. I think, does that include 35, do you know? Yes? I forgot. I think it includes us. Exactly 35, right? Well, I think it includes 35. So let me make it. So younger than 35. Say, I think a lot of you here are younger than 35. Well, you would be, if I change and to or, you would be eligible, right, for presidential candidate. If it's not and, if it's or. But actually, in reality, you are not qualified because the word between these two statements, it's and, it's not or. But say I can change it to or, then case 1, like a lot of you here are younger than 35, but you are born in the United States, so you are eligible. but also includes people like me. I am over 35, but I was not, so I'm not born in U.S. That would include me, but in reality, I'm not eligible because the requirement is in. You need a vote. But again, if it's or, I would be eligible. Now, also in case 3, because or includes, it could be, yes, people born in the U.S. and greater than or equal to 35. So that's what we actually have in real life. But if you change it to or, you could cause a lot, pretty much a lot of people will be more people will be eligible. Okay, so or union or disjunction we talked about before, not as strong as and, conjunction, and intersection. All right, so make sure you understand the difference. Don't confuse them. But this includes that. Well, that first one is what we called union. This one is what we call intersection. We don't call them conjunction, disjunction as in logics, but we have different names for sets. So take a look at what we just did. How would you define union? Definition of union. We have given 2 sets, A and B. Given 2 sets, A and B. How would you define a union of A and B? A union B. What's the definition from what we just explained, what we just did, that example?
It has to appear at least once.
Yes, appear at least once, or in other words, has to be either in A or in B, right? Okay, this way, this definition is easier for you to memorize because all you have to do is to do what? Change this symbol to or. That's all you have to do, right? So this is the definition of union. An element is in the union if this element is in A or in B. I'll put all elements, you can put X, so elements X, or all elements either in A or in B. Either in A or in B. Again, we would like you to use symbols. So how do I put symbols? All elements, I can use what symbol for that? How would you describe all elements or every element? Just use X. So every X is either in A or in B. X is in B. If you use symbols, that's why you write. Okay, so what's the definition of a union? If X is in A or X, then X will be in a union. Okay, or if X is in A union B, then X is in A or X is in B. That's the definition. And again, you've got to memorize that. Now, what about intersection? Similar to that. Intersection, the symbol we use is A intersection with B. So when we write down the definition, it's all we have to do is to change or to and. Change this to and. So all elements in A and in B. In symbols will be X is in A and X is in B. Okay. So next we're going to talk about is difference. Differences are different from numbers. So how do we do difference here? Difference means delete. Get rid of something. So if I ask you to do A minus B, now you're not going to do like subtracting numbers, like A minus D, A minus C. No, that's not how we define that. The definition of subtraction or difference of two sets is deletion. So you are going to start with the first one. Because we are subtracting B from A, right? Subtracting B from A, which means you delete elements of B from A. All right, so let's start with A. And also going to look at the B. Delete D. First thing you tell you to do is to delete a D. I don't have a D there, so you don't have to delete anything. Second thing you want to do is to delete E. So you got to get rid of that E there. Delete F, no F there. G, delete a G. So what will be deleted? E and G. And you write down whatever is left, A and C. Is that clear? Okay. Now similarly, we can do B minus A. Now what would be the answer for B minus A? It would be
E, F,
E,
D, F.
D, and F. Okay, yes, that's right. So this time, because we're subtracting A from B, which means you delete elements of A from B. Delete A, no A's. Delete C, no C. Delete E, we do have to delete this one right here. Delete E. So we delete E and G, we're left with D and F. As you can see, A minus B and B minus A, it could be completely different. Okay, so subtraction, the definition, difference, go back to put the definition there. And look at how we describe this. What elements will be in A minus B? All elements in A, but not in B, right? Okay, although when we do it, we do deletion. When we define it, the definition is, we don't really say delete the elements of B from A. That's how you do it. But the definition we say is, we found all the elements in A, but not in B. Okay, A is in A, but not in B. C is in A, but not in B. All elements in A, but not in B. I do have to put this A minus B here. Okay, if you want to use symbols, that would be X is in A, and X is not, but X is not in B. If you do B minus A, you would change, switch A and B there. Last concept is called complement. Complement is the same as doing difference. But when we do difference, you're always given two sets, you subtract them. Complement, you always do difference. So for example, what's the complement of A? You're only given one set. And the symbol we're going to use in this class is A raised to like a sort of an exponent C. In some other textbooks, they may use other symbols you may see is like A bar. But that's why we use in our statistics textbooks here, A bar. But in this class, we put A raised to C. So that means complement of A. Well, there's only one set. How do you do difference? It's the same as doing U minus A. And the U is what we just mentioned, called universal set. Universal set is the set that includes everything you are going to talk about, all the elements we are going to talk about, all those operations. So go back to that example I did. Here. Oh, right here. So go back to look at this one. So at the very beginning, when we did the A union, B, A union, A intersection with B and A minus B, we didn't use U at all. So this U right here, we didn't use it. But the only time you would use it is when you do the complement. So complement is like doing. So suppose I ask you to do A complement. Complement of A. So remember the definition is to do U minus A. The you're going to delete elements of A from U. So delete A, delete C, delete E, and delete G. So we're going to get B, D, F. Did I miss something? Delete A, C, E, and G. So I have B, D, F, right?
Yes.
Okay. And similarly, you can do complement of B. What's complement of B? So you are doing U minus B. Well, you don't have to give me the definition. This can be omitted. You can go ahead and just write down your answer. So I do delete all elements from B, from the universal set U. So I'm going to have A, B, C, A, B, C. The complement means subtraction, difference, but you only need one set to do complement. Here the definition is anything not in A. So let me write down the definition. All elements not in A. All elements not in A. You're talking about in U, all the elements in U, but not in A. If you do complement of B, then all elements in in U, but not in B. So complement means like opposite, not in there. Now we see complement means not in there. Okay, now next we are going to do another type of question. We're going to use another type to do all these four operations. We're going to use intervals. And I think this is sort of like what you did in algebra class, which we call compound inequalities. So if you did, if you've done that before, and if you understand this, that should be easy for you. So on page 261, there's another example. We have the universal set is going to be real number set R. And the set A given is all real numbers and between -1, sorry, there's not an equal sign there, less than X, less than or equal to 0. So strictly less than X. And B is all real numbers between 0 and 1, strictly less than 1. And now we want you to do a union of A and B, and intersection of A and B, and the complement of A. You may be able to just write down the answer. Can you see, if you just look at the inequalities, can you see what real numbers will be in the union of A and B? If you can't, we do what the textbook did. Draw a graph. That's what you should have learned in algebra class. So this is what we do. First, I'm going to graph all the numbers in A. All numbers in A are from -1 to 0. Open circle for -1, close the circle for 1. Well, you can use parentheses and bracket, right? Have you all learned that graphing in algebra class? Do I need to explain this? Yes? Okay.
No.
No? Okay.
No.
All right. So to do the graphing, you because this is less than, not equal to, right? So that's why I use the open circle. And at 0, it does have an equal sign. I use the close the circle. And the numbers between them, you will highlight those numbers. If you don't have two colors, go ahead and just raise the line. You can do that, right? So different ways you can do. So this graph tells me all the numbers, all the elements in A. Now let's also do all the elements for B. And I don't have another color. So it's between 0 and 1. Starting from 0 and it's closed because there's an equal sign. I'm trying to use this color here. And at 1, there's not an equal sign, open circle. And all the numbers from here to here. Or you can use a red color here, highlight those numbers. Okay, now, so we can see graphically what numbers are in A. The blue ones, all the elements in A, these numbers, from here to here, including 0, not including -1. All the red colored numbers, they are elements in B. So go back to the question, A union B. Think about the definition. Union means English word what?
And
Or.
Or, okay? It's or. Union is or. Intersection is and. That's or, that's and. So what would be the answer for A union B? Yes. So, as you can see, union, if you remember, what I said appears once, right? Where the numbers in one color. That would either here or there. So that means you can take all of them from -1 to +1. Be careful about those equal signs because -1 is not in A, not in B. It cannot be in the union because whatever in union has to be either in A or in B. If it's not in any of them, you cannot put them in the union. And 0 is in both of them, of course, they're going to be in the union. At 1, it's not included because 1 is not in B and not in A. So pay attention to those boundaries. Now, what about intersection? Only one answer, right? 0. 0 is the only number that is colored twice, blue and red. And 0 is the only one in both A and B. So when you write down the answer, you could just put it like this, 0. I mean, of course, if you say, can I follow this, say x is element of R and x equals 0, you can, but this is good enough. But the other way to write it would be, long way to put it is going to be like this. You try to follow that format, but this is good. And complement. Complement, remember, complement means any number not in A. Complement pretty much means not in A. So what numbers are not in A? If you look at the graph, green color, that's A. What numbers are not in A? Here, right? All of them here, or here, right? So there are two sides, don't forget. So by drawing the graph, it makes problem easier. I think some of you may be able to do it without drawing the graph. Drawing the graph will be easier. So let's write on the answer. That would be 2 parts. X is less than -1 or x is greater than 1. Equal. We gotta both put an equal sign at -1. Does anybody know why I put an equal sign there? Yes. Okay. But remember, complement means not in A. Well, -1 is not in A, right? Because there's an open circle. If it's not in A, then it should be in the complement. So that's why we got to put an equal sign there. The same for 1. 1 is not in A. That's why 1 should be in the complement. Wait, hold on. I'm sorry. Can you speak up a little bit? Oh, yes, you're right. I'm sorry. I messed it up. Okay. Because we're looking at A. We're not looking at B, remember? Okay, so the numbers are, well, I have to get rid of equal sign then. Sorry. Okay. So x is greater than 0. Okay. So when we are doing complements of A, it has nothing to do with B. So probably because I put this here, I also confused myself. So maybe you could redo it, maybe it'll be easier. You don't have to, just if you pay attention here. So this is A. Complement, when you do complement of A, it has nothing to do with B. So that would be all these numbers here, less than negative or equal to -1, and all those numbers there. not including 0, because 0 is equal to 0 is in A, right? Is 0 in A? Look, it's close, right? Okay. If 0 is in A, then it cannot be in the complement. Okay. Complement is anything not in A. So that's why I have to get rid of the equal sign, greater than 0. Any question? You can use the graph to help you to do this. This is something you do in algebra class, and I actually just taught this in last week in D05 class, and in D1200 we also talked about this. But we don't use those symbols. We just ask you, okay, what is this and that? I think the one in algebra is a little easier than this, but here we have something more complicated. But another thing I want to mention is, please, some students try to combine these two into one symbol, just like that, and say, look, I can put it just less than for that, right? Can we do the same thing? Like, for example, I can do, well, x is less than or equal to -1. I can switch then to get -1 is greater than or equal to x. And then x is greater than 0. Can I put them together? No. Okay, please don't do that. Because first of all, if you put it like this, is -1 greater than 0? No. If you say -1 is greater than or equal to x, greater than 0, that's not true. Because -1 cannot be greater than 0. Secondly, whenever you use two inequalities together, that means and. Means x, -1 is greater than or equal to x, and x is greater than 0. But if we're not doing and, you're doing or. If it's and, there will be no solution. How can you have a number smaller than -1 but also greater than 0? Is that possible? If a number is greater than 0, it's positive. It cannot be less than or equal to 1, right? That's why you cannot put an and here. It has to be or. So in the past, I think sometimes I did see some students put this way, especially in algebra class, they thought they could just put the same way, but this is not correct. So you do have to put them in two separate inequalities, because from the graph you can see there are two separate. It cannot be and. It's either here or there. You cannot say here and there, because you cannot find a number greater than 0 and less than -1. Okay, so that's a little something there. Well, next thing we have two more concepts that we got to talk about. The last two definitions in this section, number 4. One thing, this is called a product. It can be considered as product operations. We call them product. Maybe we can just go ahead. I'm sorry, just list it as operation 5, product. When you're given two sets, A times B. So we did A minus B. It's like deletion. What's A times B? I'm going to have to give you a different example, because A times B could be very, very long if I use the previous one. It's going to be very tedious to do that one if I want to do A times B. Because the way we do A times B is like a point. Think of this. Let me give you A as 1, 2. B as 1, 2, 3. So what does A times B mean? Not a multiplication. We're not going to do multiplication. You cannot do 1 times 1 is 1, 1 times 2 is 2, 1 times no. That's not how we do that. The definition of sets is you're going to think of the A as x coordinates, B as y coordinates. So you're going to come up with a bunch of points. The first element the x coordinate has to come from the first one, A. So it's 1. Second, y coordinate has to come from the second one, B. So you get a 1, 1. If I use this as my x coordinate, remember these are your x coordinates, these are your y coordinates. You're going to have 1, 1, 1, 2, 1, 3. And you could use 2 as your x coordinates. You're going to get 2, 1, 2, 2, 2, 3. 2, 1, 2, 2, 2, 3. Pay attention to the symbols. For set, we use curly brackets. For points, if you remember from algebra class or calculus class, for any points, we use parentheses because the order matters. When you switch x coordinate and y coordinate, you get a different point. For example, 1, 2, and 2, 1, are they the same point? No. I can show you a little quick in x, y coordinate. 1, 2 is this point, 1, 2. What's 2, 1? 2, 1 is this point, right? So when you switch x, y, you get a different element. So that's what we do in math. Parentheses usually for ordered numbers. Brackets, no order, okay? Previously, although when I listed the elements in A, I did alphabetic order A, C, E, G. You really didn't have to do that. If you put A, E, G, C, any random order is fine. They're still going to be the same, okay? So curly brackets for no orders and parentheses for orders. Because I noticed that in the past, some students put curly brackets here, curly brackets here, curly brackets there. That's not correct. Make sure you use parentheses for every point. So product here, it's also called a Cartesian product. If you remember in calculus class or algebra class, we have this plane, we call it XY plane. We also call it Cartesian plane. From history of math, you should have learned about this mathematician, Descartes. So he sort of created this plane, XY coordinate system. So this idea is very similar to that. So that's why we call it Cartesian product. Is that clear? Okay. I guess I have one more thing that I have to talk about on Wednesday. Okay, and that's all for today. Wait, say it again?
We don't have any syllabus on it. Office hours, conference days.
Your meeting has ended.